Thank you very much for a kind introduction. Thank you everyone here for, I hope you enjoy. I don't intend to be too specific on the topics, but I wanna point out what we've been doing, like giving you a general overview of our division, and also well, flashing at least some opportunities that we can straight our connections. Like Juarez mentioned just now, it's been a great partnership with him. We definitely get along. It's like selecting different people and say, look, you're gonna get married next month, and we have higher expectations of those and of this wedding and everything. So as Juarez just mentioned, we have a big challenge together with big opportunity to come up. And that's very exciting. This is different and new for every one of us, but I think that we have like a very interesting future. And we largely depend on everyone in this room here from all levels, researchers, PIs, co-PIs, you guys. If we can work together and we understand our goals and we commit to them, I think that we have a very, very long and profitable partnership for all the stakeholders involved in this journey. So without any, my division's a little bit mine in the tenderness of saying mine, because we are very democratic there. We divided our division in two institutions. We are half, I'm based at IPEN. IPEN is, well, I'm gonna tell a few words about IPEN later so you don't get confused never more that IPEN is IPT. So that's my major goal here. And the second one is a federal university, Fábio C. And from there comes Professor André Santa Rosa Ferlauto, which is the co-coordinator of my division. So we basically take all the decisions concerning the organization together. And well, my division is about methane conversion. And it's a little bit more difficult to explain for everyone, or for the general public, it's a little bit more challenging, because when you talk about the first two divisions, you can right away think about producing clean energies. Even the name of the center has this reference of new energies, but we are not actually producing energy. And sometimes it's a little bit difficult to explain what we do. But I just found out a very interesting short 1-minute video that I'd like to show you and give you exactly what I would take slides and slides to show you, okay? So I think they're gonna be more effective showing that in 1 minute. I hope it never works, but yeah. So that's it. So this is a short video from the International Energy Agency. It's always very interesting suggestions from YouTube, but we skip to the next slide. They really want us to watch some music, but so this is basically what we have to do here. Our division is committed to the conversion of methane to other chemicals that could be used as building blocks or would have higher added value than methane itself. So here we are. Sorry. So what is the context? So we're embedded in this. Shell is very famous for doing those future scenarios. Exactly. And we are, our center is actually a commitment made by Shell today to make this transition to this future energy mix, this is 2070, right? So we have like 50 years. And they build up this future scenario. It's not like futurology, but there is a lot of science there as well. And the idea is, one of the commitments here is like, what do we have to do if you want to limit warming of our planet, temperature increase in 2 degrees C. So if you want to do that, this is one of the results of their simulations. You guys do simulations, so this is one sort of scientific simulation. And if they wanted to do that, we have to do certain actions right now. And that's what Shell wants from us. They want us to help them to make this transition. So this is the global scenario of our center. And specifically, back to my division again, we have 2 basic, very important ingredients. In that matrix in 2070 that I just showed you, Shell believes that electrical energy will be available and affordable. So basically coming from renewables, either photovoltaics or wind. So energy we have. We can even use some energy as an ingredient for our reactions. That's the point. And the second ingredient is, there is a lot of methane in the planet right now. There is a lot. When I mean a lot, there is like methane coming up from all holes possible everywhere. Shale gas in the US, and even in our pre-salt reserves in Brazil, they have a lot of gas. A lot of gas. A lot of gas. A lot. Right now at the pre-salt reserves, just for you to know, we are re-injecting gas, which is basically methane down the wells again, just to increase the pressure and increase the oil release from those deep water reserves that we have. At this point, methane cannot come all the way from the pre-salt oil fields to the coast. It's being stored down the ocean. But what do we do with methane? Basically, humanity only burn it, basically, right? So methane produces energy. It's the easiest way. Well, it's a very, now I'm a chemistry place here, so you know very well, this is a very stable molecule. It's not polarized, it's like completely stable. It's like people call it the diamond of the gases. So that's why getting this molecule to react, or either go all the way and burn it, or stop in between somewhere to have other molecules, it's a very challenging reactions, very, very challenging reactions. And this is where we are. That's what we want to do. We have two focus. We are focusing like a partially oxidized version of methane alcohol, so it's methanol. That could be interesting for transportation, could be used for storage. That'll be interesting. And also as a building block of other molecules as well for chemical industry. And we are also thinking about ethylene, polyethylene. It goes to the plastics, you know, we go to a lot of applications like the video showed. And eventually, hydrogen would be a product of our division as well. And we're going to do it, instead of doing the regular catalytic reactions, we are proposing new electrochemical pathways, trying to control those reactions using also electrical potential. So this is the basic philosophy of our project, okay? Yeah, those are like a general scheme of different reactions that are known and studied for methane. You have the low temperature ones and the high temperature ones. I'll always keep that to the, but we are focused. This is a slide I took from my presentation last week, and we are in my project. I take care of one of the projects, and we are taking care of high temperature reactions, okay? But there's people also looking at the low. I'm gonna tell you a little bit more. Well, this is basically a joke. Our ingredients are methane, water. There's always a little bit of hydrogen coming up. We're gonna spark some electrical field here. So this is just like creating life. This is the basically Miller-Urey experiments when they are trying to simulate the creation of life in the planet. Very, very challenging topic. So where are we coming from? Our department is, we are from IPEN, Instituto de Pesquisas Energéticas e Nucleares. A gente fica dentro da USP, inside São Paulo campus of USP University, but we are a federal institute, And like I said before, we have nothing to do with Instituto de Pesquisas Tecnológicas and also nothing to do with Instituto de Pesos e Medidas com M no final. Tá? E nós somos dos departamentos lá. We are the youngest and the smallest department, actually. We've been created 13 years ago with very close connections to people from this department here from electrochemistry, and we are working a lot of fuel cells. What we're doing in this project, we are basically using fuel cells not only anymore for producing power, but also for as a electrochemical reactor. Okay? So that's the idea. What do we do there? We do basic science. We do a lot of synthesis. We have nanomaterials. We do basic material science, I would say. But we also go all the way to the small devices. So we test them, we test unit cells. And there was a time that we were even like building up and making stacks, trying to produce power off of those. So we are producing fuel cells running on hydrogen. And well, we came up all the way up to 5 kilowatts with all design. But those projects are gone. There's no money anymore to invest in technology. So we came back more to the basic science. In the last few years, one very important product is the students. We are part of USP as a graduate student program. We are CAP's 6th grade program associated to USP. We are USP. If you go to USP and you want to do anything about nuclear technology, you're going to find IPEN. Although there are many, many different things over there. There are many, many groups working with things that are not nuclear directly related like us. And a second very important activity that we have is like dealing with ethanol. There was a lot of effort trying to use ethanol as a fuel for fuel cells, but also like obtaining hydrogen out of ethanol, so ethanol reforming. So this is another branch of our group. So we basically have our high temperature group, low temperature group, and gas mixtures analysis group. We have 3 groups over there. We are 10 people. 4 of them are what we call principal researchers. That we mean we are supervisors in our program at USP. And at this point, we have around 35 students all the way from graduação to postdocs, okay? Undergraduates all the way to postdocs. We have some projects going on. Most of them are getting close to an end because we are very, very busy with the CINE. 2 of them are those. FINEP, Cibratec, we have a thematic FAPESP project on methanol fuel cells. And we are part of another center already. We have a project in the older brother of CINE, which is called our CGI, Research Center for Gas Innovation, which is based at the Polytechnic School in São Paulo University. Just rough numbers here to show you. We have been publishing last year's around 100 papers. There are some patents coming up again as a result of our technology developments over there. And those 4 supervisors have produced around 15 PhDs in the last 5 years. Those are the projects of our divisions. We have 6 projects. We organize them as each one of them has a co-PI with a project coordinator. There is always an assistant investigator and students, which are not listed here, and usually they have an international collaborator as well. So there is a network of people that we've been contributing and collaborating in the few years. So those are not new collaborations. Those are collaborations that are already going on with the traditional collaborations between us and our PIs. We organized ourselves like a mini version of the hub, of the center itself. We have also a committee, our executive committee, which is formed by myself and the project coordinators of the 6 projects, okay? So this is more or less like we organize ourselves. So this is the future scenario. We have electricity, we have methane, and we have our projects, and then at the end of the day, we want to come up with monetized natural gas. And here, I will give you some examples. Those to the left, this left column, is the low temperature projects, and to the right are the higher temperature projects, okay? I'll talk about some of them. This is a very interesting project. This is a composite material. There's 2 phases. One that transports oxygen ions. It's a oxygen ion conductor that we're going to mix with a carbonate ions conductor. And the idea is that we can separate separate what? So natural gas coming from the pre-salt reserves comes with a lot of CO2. Basically, the composition of the gas of our reserves is similar to biogas. It's about almost half of it comes with CO2. So if you want to work, you have to separate those. And this is a separation membrane project. We have another project with a photocatalytic project, very similar to what Division 1 is performing, but we want to put together with the water splitting, so we are producing hydrogen, but we want to activate methane into methyl radicals in order to have the good catalyst here and get at the end of the day with some ethylene. Okay. And two other projects are dealing with the electrochemical reactors, basically at low temperature and high temperature. At low temperature, people are looking at producing hydrogen peroxide in situ to oxidize, because this is one of the routes to get methane oxidized. And they want to produce peroxide in situ inside this fuel cell reactor-like reactor, and get to reactor and getting methanol as a product. So this is one of the ideas going on. We've been working a lot. At this point we have, well, those researches, those projects are fairly new, basically, for all the researchers in our division. So a first step in our division was build up the facilities. So we spent a lot of time in the last year doing a lot of importation process, lab preparations, installation of gas lines, and this kind of support work in order to get our facilities running. And but a good news also that we came up with with an interaction. Well, actually, FAPESP copies this format of engineering research centers. CINE is within FAPESP context is an engineering research center, and it's actually this model is copied from NSF, from National Science Foundation in the United States, and they have their engineering centers over there as well. CSTAR is one of them. And those guys, they are working with very similar topics. They have the shale gas, of course. The Americans are not very worried about methane. They're gonna really burn it. They don't care much to produce energy, but the shale gas comes with a lot of other components, such as higher order hydrocarbons, and they want to transform those into fuels, ideally gasoline at the end of the day. So they share some common problems as we, and we were very lucky to get in touch with them, and we are starting already some collaboration projects. Actually, we got a sprint project that was recently approved this year. So this is also something interesting. Like I told you, now we are like doing a lot of work. These labs are pretty much done here. These were the ones doing the photocatalytic work, but those are the boxes with the gas analysis systems that are going to be installed, for instance, in the high temperature reactors that are still under production. They're going to be delivered at the end of the year only. And yeah, this is not very important. We're still installing the gas. These are our labs that are being prepared for this project. They are advancing. We still have some problems, bureaucratic ones. In order to get things done, it's very, very painful. But talking about the science, we've done something like a meta-analysis, like Professor showed us about the perovskites, and we are like, well, what is happening with methane conversion? What are the number of papers? And there is an increase. It's not like the same hype as perovskites, but there is indeed an increase. The thing is that if you split those also into what kind of papers are those, you basically find two main routes for methane conversion, either the OCM, the oxidative coupling of methane, or dehydroaromatization. So the non-oxidative methane conversion. And both, well, they had like a valley here, but they're growing up again, stepping up here as a result of the shale gas reserves in the United States. This is like reflecting the American interest in this component. And if you look only, those are only science and nature papers from maybe 2018, 2019. And they are popping up very, very interesting works. So it is a very interesting field for science and innovation. We have like you guys, we also struggle and try to put people together. So there is a lot of effort trying to make a divisions, putting those two teams as one team. We made in March this year, we made a first internal workshop. This was basically the audience back then, and it was very important for us to prove and get the enforce project interactions. We have projects at low temperature. They are taking care of membrane side, but also the electrocatalysis. And there are people like putting those together and coming up with a device. So we have clear interactions between projects. That's what I want to show. We have the high temperature projects as well, which share also common problems. And yeah, we definitely want to promote. That's something that we have to work on not only the workshops, the internal workshops of the divisions, but also thematic workshops in which people come together to discuss one specific problem, or at least some similarities, so within a certain scope. We suggest some topics. We have some, for instance, some methane activation. It's an interesting topic for us. Composite materials, porous structures are interesting. Yeah, so this is one of the ideas. And last week we promoted the second workshop. And we have like 2 days. The first day we kept like here, maybe we made our internal workshop. Only people from our divisions, all the students presented their works, and we discussed many ideas come up. And then the second day we had some guests. Professor Fábio from Fábio C was representing Division 1. We had Professor Gustavo Dalbeck from Unicamp from Division 2. And unfortunately, Juarez could not attend. That was a we missed him a lot, actually, his ideas and discussions. So in the second day, we also made like a poster session and working groups. We divide people in different groups in order to come up with the working groups proposal. We came up with 6 working group proposals. This is trying to bring the other divisions together with us. Those are suggestions that were in a very informal and free, is a brainstorm from different teams that people set together. That was very interesting. Professor Gustavo Dalbeck went home, already had a couple of samples in his pocket to test and things like that. So we try to capture those interactions here. Very short documents that we are preparing now. And well, the first thing that we identified was like a huge growth of our division. I want to show you here very briefly some results, just to eventually point out some of the topics that could be interesting for having. There is an effort, like Juarez said, that the people from the theoretical division, the computational materials division, to interact with us, and we are very willing to make the same effort to bring you guys. We are really interested to get the input, that very important inputs that you can provide to our problems. And from all of those projects that I showed, the 6 projects that I've showed, each one of them has a particular interesting material science problem. At the end of the day, we want to understand about diffusion in solids, how to keep a porous structure or small grain size of materials, oxides at high temperature. This is something we have a lot of Syria-based materials, how Syria interacts with methane, what would be very strong and interesting absorption points or sites for methane in Syria. If the dopants of Syria is always connected with a dopant in order to increase the number of oxygen vacancies. So this is also an interesting topic for us. How to get methane activated. This is a very challenging topic. So on project 10, like I said, it's a composite materials. We try to put 2 very different materials. There is Syria gadolinium doped Syria, and they have to make a porous skeleton in order to have mechanical stability to build up this ceramic membrane. and from the porous structure, they will impregnate this with the molten carbonate, because the molten carbonate will be the the carbonate ion transport paths. Like I told you, this is the separation gas membrane project. And well, there's a lot of ceramic processing over there, and people are using electric field assisted. So I don't know if you're familiar with material science. We start with a powder, and then we put that in kind of a shape, either pellet or, well, different techniques. And then you have to sinter to make it mechanical stable. And people from this project, they are developing, usually you do that in a furnace, like traditional ceramic. High temperature, 1500 C, for instance, to get ceria as a solid body. And here people are using an electric assisted technique. So instead of increasing the temperature, they put the temperatures, mild temperatures, like 500 C, and then they apply the electric current in this material. So then you can come up with different microstructures that could be interesting for the second step of impregnation of a molten carbonate. So this is one of the projects, one of the results. I'm going to skip that. There is also another project, which is like there's deep polymeric membrane development. People are starting with ETFE polymers, and they go to, at IPEN, we are a nuclear facility, so we have irradiation over there. So what people do, they irradiate those polymers to create active sites. It's called a process grafting. And there they can come up with the chemistry and attach other groups that are actually going to be functionalized for having the specific counter ion that they want to transport in this membrane. So people over there are developing new ionic conductors, and that's the way they do deep polymer science here. So there's one group of low temperature fuel cell-like reactors. They are working with the membranes. So this is also a very interesting topic. And those teams of low temperature, they are developing inoperando techniques. So they build up small modules of those electrochemical reactors, and they put that inside different equipment. For instance, the infrared spectrometer, and they can correlate different. So they basically get those membranes, like I showed you, or similar ones, and they deposit in both sides electrocatalysts. Those electrocatalysts will be nanoparticles of different metals, usually, for instance, platinum, palladium, supported on high surface material, usually carbon-based materials. So those devices, those electrochemical reactors, you put them to react inside those analytical chambers, and we can, depending on the potential of this working electrochemical cell reactor, we can map the different products by inoperando techniques, such as fast Fourier infrared spectrometry, or for instance, now we are doing about the same thing using Raman spectrometer. Those are the kind of data that we can collect at this point. So eventually, can in different potentials working of the cell, we can tell different products or. I don't know about time, Juarez. How am I doing? It's okay? Good. Well, I don't. This is the. Okay. No microfone. Ok. Para vocês entenderem um pouco melhor, essa transparência foi para português e eu também. But this is basically this is the same idea. It's an electrochemical reactor But this is what we call a solid electrochemical reactor, because that goes to high temperature. Again, we go to ceramic materials because we work at above 600 here, okay? From 600 to 1000 if you want. And this is the project that I'm more technically involved in terms of research. That's my playground. And okay, I can skip it, I can tell you what. But we are here. We're basically trying to get methane as a direct path to olefins. Well, at the end of the day, it's not a microphone anymore. So that's one of our goals. That's what we proposed in the beginning of our project. And what is the background? I want to show you a little bit of the background. Where is our past connecting to this project? Myself, I've been working with solid oxide fuel cells. We call it SOFCs. SOFCs are ceramic fuel cells. They work up from 600 up. And basically, you do the electrochemical reaction of a hydrogen oxidation. In one side, you have a ionic conductor, the classical one. So basically, you have air, hydrogen, and you produce water and energy. So this is spontaneous reaction. And this assemble of those three materials here, that's like the hardcore of the fuel cell. Those three materials together, they have a very interesting property. You can just like using the very same chemistry, and you can reverse the reaction. So instead of producing power, you can use power, and you're gonna have a solid oxide electrolyzer cell. So you run water and oxygen, and you apply a current, and you're gonna have some hydrogen. You produce hydrogen out of water. It's electrolyzer. And those materials are being developed in this context because, could be very, very interesting having, when working with the renewables, either wind or photovoltaics. I don't know which one of you already had the chance of having a solar panel. If there is light. This is and if you just move your hand over and make a little shadow over the panel, have you ever tried that? Have a multimeter, have a solar panel, and then you just pass your hand in between the source of light and the panel, and you're gonna see that the current really drops. So if there is like a cloud, you're not gonna get your iPhone charged, or your shower is gonna be really difficult. So what people have here, so those devices are strong competitors in energy storage. So at this point, humanity is doing relatively well in terms of producing energy. With the solar photovoltaics, we can get a lot of energy. But storing energy is another issue. It's really complicated. So what those materials are proposed as, those devices are proposed. So let's imagine that you have during the day a lot of sunlight outside. So you have a lot of wind, and eventually you can produce a lot of power that eventually is not used. It's not the time that people need the electrical power. So you need to store. You need to store for the night, let's say. And what you could do, instead of just not using this energy, you could use it as electrolyzer. And then at night, you could run in the reverse mode and produce power. In a very clean, zero carbon here, okay? So that's the context. And that was the step before proposing those electrochemical cells as chemical reactors, okay? So that's why we have this whole idea of our division goes around this. And people are doing, for instance, now co-electrolysis of both CO2 and water, for instance. There's a lot of research going on here. So they can produce syngas as one of the products here. This is one of the things that you could do with those systems. And from syngas on, you can go for synthetic fuels, different reactions, okay? And why they do that? If you take, particularly in that case of high temperature fuel cells, or particularly high temperature solid electrolyte reactors, if you increase the temperature, the heat demand for electrolysis, this is specifically for electrolysis, right? CO2 electrolysis. And the electrical energy demands goes down, but the heat demand goes up. So actually, more or less, it's constant, the enthalpy of this reaction. So that's why people are looking at those high temperature devices for those reactions. And what we could do with the solid state reactors? We have different materials that can transport oxygen ions. Everyone, in every car, you have an oxygen ion conductor over there. It's people call it the lambda sensor. It actually measures the content of oxygen of the mixture. And so, like, then there is electronics saying to your engines to balance the mixture between air and fuel. And this is the same material here. This is basically yttrium stabilized zirconia. In some cases, ceria-doped, ceria-based oxides. There's a lot of material that can transport oxygen ions. But believe it or not, there are also ceramics, different kinds of ceramics that can transport protons as well. There's a lot of research right now at these protonic fuel cells. I showed you the examples before with the classical oxygen content, oxygen conducting ions, but you can use also proton conducting. And we have the membranes, actually materials that are very, very special because they can conduct both a little bit of oxygen ions, but they can also transport electrons. That's what we call mixed ionic electronic conductors. We can also use this kind of materials as a separate. And why do you need a membrane? So that's what I want to show you. Because there's a lot of electrochemistry done in liquids, right? But then everything is like a soup, literally, how you separate your products. This is one of the points. And if you work with, like I call, wet electrochemistry, at the end of the day, you have water. So you're limited in terms of the electric potential that you can use, because eventually you have oxygen or hydrogen evolution, right? So in those kind of reactors, in principle, we have more room to investigate different potentials, right? And then you can come up with different concepts. I can have, for instance, two chemicals coming together and producing A and B reacting, producing C and D, and I have a D membrane here. So let's say I can really shift the balance, the equilibrium of the reaction towards the products here. If I can separate one of the components, one of the products of these reactions. So this is one of the type. Or I can use, for instance, like I told you, if you react methane with oxygen, basically you're going to have like, boom, you burn it. You're going to have hydrogen and CO2, right? But if I can eventually have A and control with the electrical potential very, very carefully, I can give the system very small doses of my reactants here. So I can inject very small and controlled amounts of the reacting species to these reactions. That's the idea. Those are the main ideas of having those electrochemical reactors, okay? And then one of the examples is getting this kind of reaction. This would be our dream. This is what actually we proposed in this project. And yeah, how can I do that? Well, if you look to those materials, I told you like three basic components. We have an anode, electrolyte, and a cathode, okay? But if you look at the state of the art of those devices, they can be pretty complicated, very, very elaborated microstructures. There is a lot of materials engineering going on there. If you look at the microstructure of those devices, it can be very, very challenging to control those materials. So you need a dense membrane, a dense electrolyte, like for instance, yttrium stabilized zirconia. It's an oxygen ion conductor. But then you need two porous electrodes. You need a cathode and an anode. with different microstructures. So coming up with those devices requires a lot of expertise and materials processing. And then in the end of the day, you have something like that. This is a unit cell. For instance, here, the classical one, it's an anode-supported cell. We call it anode-supported cell. And here you see the mechanical support, which is the bottom part of this, which is the anode. On the top of it, you see you cannot see actually the electrolyte because it's a very thin, 10 micros thick, so it's transparent, pretty dense. And then on top of it, you have the cathode, which is the black part. So when that goes to the furnace, 600 degrees, 800, 1000 degrees C. I'm going to skip. So in the infrastructure for this project, it's basically consists of like the gas analysis system. This is the one that is already running for the photocatalytic project. And this electrochemical reactor here, which is a test bench for this high temperature solid state reactor. They're going to be connected together. They're going to be in this room. Right now at this point we are struggling. We have a lot already done, but we're still fighting with the bureaucracy to get the gas lines here. It's not easy sometimes. And most of the times. And yeah, and this was a very motivating paper, but a little bit frustrating because basically our ideas are captured in this recent paper that was published in Nature Communication earlier this year. And they basically proposed the things that we proposed. And very interesting. They add up something very interesting, which is also something that I've been working with, and then maybe some of you guys got interested in that. Let me briefly show time. I'm doing good with time. Okay, so imagine, guys, that you have like a perovskite type of structure, AbO3. Paper, one of the most common ways of getting oxides in this planet is the AbO3, but you can have like slightly different data. You can have a double perovskite. It's like AA prime, BB prime, O6. Okay, this is sort of the material that we have here, but on top of that, you can come up and you can dope. So you can add chemical substitution, you can add another atom over there, okay? And there's a lot of very interesting new work coming on what we call exsolution of nanoparticles. They add some more like iron here. So you see that it's slightly out of balance here, okay? There is plus here. What happens here is that when you treat those materials in a very reducing condition, high temperature, under hydrogen flux, actually iron goes out of the structure, out of this perovskite structure, and pins as nanoparticles on the surface of the ceramic matrix, let's call. So that's what they call exsolution. And this is a very interesting because, well, there are many, many things that are interesting here. First of all is that you have a very homogeneous distribution of those nanoparticles because they were, firstly, they were inside the structure. They were part of the chemistry of it was single phase material, okay? So they are very homogeneously distributed over the surface, and they come up from inside of the crystal to the surface. So that means that those particles are kind of pinned here. They cannot move. So that means that at high temperature, there's no much of coalescence. They hold their size. Instead of if you have like small nanoparticles that you just impregnated and you put at high temperature catalysis, people know that very well, those particles tend to grow. And then you lose surface area and then you lose activity. So that's the classical thing of catalysis. What happens here, those particles are more like, they cannot move a lot. Second thing is that they have a lot of surface area here, because what happens here is that very interesting. We have a very, very interesting concept. In order to have those electrochemical reactions, you need all the ingredients in one, what we call triple phase boundary. All the ingredients must meet. They have to be all together. The electrons, the ions, and the gases, they have to be here. And here you have the whole perimeter of those particles serving at this triple phase boundaries. So you actually increase the chance of your reactions to occur. And not only that, you know, that there is one thing which is like reacting methane, for instance, with oxygen, oxygen O2. It's one kind of reaction. What you want here, those solid state reactors, it's something else. We want to react methane with O2 minus. It's an oxygen ion, which is much more reactive. And this is exactly what you want here. So that's one of the key success of those groups. They proposed and they had very interesting results. Just showing you, and what they do, basically they investigate different stoichiometries of iron here, and they find out optimal one, and they operate those reactors at different potential, and that's exactly what they have. They have the gas analysis, so they know how much ethane, ethylene, everything they're producing. And this is pretty much what we propose to do. Okay. What we've been doing at this point, so we cannot do all those measurements because we don't have our experimental setup all done at this point. We are doing a lot of synthesis, trying to prepare the components of those cells. And one of the things that we have been doing is also very interesting for the theoreticians here. We have been producing ceria, but not only ceria, we are trying to control the shape of those crystals. So very, very smart chemistry guys like you, they come up with this hydrothermal reactions, and they can control it. Only by controlling temperature, they can come up with different shapes. Very, very interesting. And, you know, very beautiful. I love it. It's like the nanocubes. This is like, if I would be a theoretician, I would like to say, Fábio, let's talk now. Look at this. Okay. So those cubes and those nanorods are produced by the hydrothermal, and we are using this. Those are single phase. We can produce them with different dopants, ceria gadolinium, samaria dopant, ceria, different materials. They're crystalline, single phase. They work nice. But at the point of like a ceramist, I'm a physicist, but I have this background working with ceramics a long time in my life. And what happens if you're gonna like to try to pack those particles? What happens if you have shape? People have been trying to sinter materials, like how to come from a powder to a ceramic body. Ceramic comes from the word in Greek, keramos. Keramos is basically fire. So when you work with ceramics, there's always a step at high temperature. We need a sintering. Sintering is like putting the powder together and make it as a solid block. So what happens if we have such different shapes? Does it influence somehow sintering of material? Can I have a because people want sometimes very dense membranes, but sometimes you want also very porous electrodes. So we have to deal with both in our case here. So we've done some experimental with the nanorods, nanocubes, and we compared that with random nanoparticles, and we come up with very interesting results. We have our nanorods that are sintering for ceria-based materials at rather low temperatures, like 1,000 something, 1,100 to 1,000 degrees C. This is rather low for ceria-based oxides, and they go up very, very high densities here to the theoretical densities. This is like the mass. Those are like the solid state diffusion process going on in those materials, and we activate different ones. So the nanorods, they are very, very, very defective surface, very high surface area, and a lot of defects, so they're willing to move. Those are the defects that are going to move when you increase the temperature. On the other hand, the cubes, so it's very, very controlled faces of the crystals, very, very low energy, very, very low energy. So when you put them together and you increase the temperature, at the end of the day, really nothing happens. They stay rather porous, even at like 1,400 degrees C, which is very cool for catalysis if you think about it. Okay. So this is what we've been working at this point. Those are the resulting microstructure. This is nanorods. After 10 hours, I have, well, this is 0.1 hour. This is very, very quick at 1,400 C. We sinter those particles. They already get very dense. At 10 hours, you have like a beautiful microstructure, very similar to the nanoparticles, random shape. But the nanocubes, no. This is 0.1 hour, 0.10 hours. In 10 hours, you have a rather porous structure, which can be very interesting, like I said again, with catalysis, okay? Yeah, and those are problems that are shared between different projects of our divisions. Those are the high temperature people. Yeah. Yeah, and we, like I said, mentioned before, we are doing we want to expand CINE. I personally believe in collaboration. So far in my life, I have collaborated with many people, and I have to say that most of them became my friends at the end of the day. So actually, people that I've worked back on my PhD, they're still working with me today, and are even involved in this project. So we had the chance of getting people from C-STAR together with us. As a big coincidence, C-STAR is this engineering research center from NSF. It's also coordinated by a guy named Fábio. He's a Brazilian guy in Purdue University. And this is not important here. So there are people of our, some collaboration, I mean, BRAPA people here, and also from Jülich Research Center in Germany. They're still already going on research center with them. So I've been talking a lot. We at this point, we are getting done our labs and setting up our experimental setups. There's already some research going on. We are hiring people. We need smart students with us. So if you know people that are willing to move to São Paulo is cool, believe me. It's not that scary as it seems sometimes, but can be a very, very live place and interesting to work. And yes, we are building up a center. That's my final message, and I hope to collaborate. And thank you very much for your invitation. It's a great pleasure being here. Thank you very much.